The next lecture is section 4.6 in your textbook. It's on elastic potential energy. So one important type of potential energy is the potential energy that is stored in springs. And we call this elastic potential energy. Now, when we have a spring in its relaxed state, it doesn't store any energy. So if there is imagine a spring that's not stretched or compressed, it doesn't have any force that it is either holding. In the relaxed state, we have we have a variable that we introduce called that is x. That's the displacement of the spring. And when x is positive, you can consider that as being a stretched spring, and when x is negative, it could be a compressed spring. When x is 0, the force of the spring is 0. Now we could pull the spring, and when we pull on the spring, we make x non-zero, we make it positive. There's a restorative force that the spring has that pulls in the opposite direction. This is the force that tries to bring the spring back to its original position. And we could have the other situation where we push on a spring, we compress a spring. Our x becomes negative in this case. And now there's the restorative force of the spring, which pushes the spring back to its original position. So according to Newton's third law of motion, the force exerted by the object that is applying the force to the spring is equal and opposite of the force that the spring exerts on that object. So that F spring is equal to either F pull or F push. So we call that a restorative force because it tends to restore the spring back to its original length or its natural length. Now there was a scientist who we'll learn quite a bit about in this course. His name was Robert Hooke. And Robert Hooke ended up determining that there is a relationship between the applied force and the extension, or the either stretch or compression of a spring. And if you see the graph there, you see that it is linear. This tells us that Fa is equal to K of x. And that K is something we call a spring constant. So copy this slide down. Hooke's law, the Fx, or the Fs, depending on which convention you're using, is the force exerted by the spring. K is the spring constant. It's measured in newtons per meter. And delta x is the displacement of the spring from its rest position. Now, the higher the K value, the more stiff the spring. That'd be the more difficult it is to stretch or compress. Another thing to note is that Fx is a restorative force, so it's always pushing in the opposite direction of the displacement. Now in this graph, if you remember from your grade 9 math courses, your slope of this linear function, this is a y equals mx plus b, where our b is 0, so it's y equals mx. And if you consider y to be fa, and that m would then be the k. So the slope of this graph would represent the spring constant. And the greater the k, the higher the slope is. That also implies the greater the stiffness. So if we have a linear function that has a very high k value, it would the higher the k value, the more it approaches a vertical line. It starts to have a greater slope. So here's a question. It says here, we have a bow. We're pulling back on the bow with a force of 133 newtons. And we are asked to find out what is the spring constant of this if the pullback draw is 71 centimeters. Quite often you'll get these questions in centimeters. You'll have to change that to meters. So if this is F equals K delta X, F is 133. To isolate for K, we have to divide this by delta X. So we divide by 0.71. We end up with 187. And we round for two significant digits because the 71 is our limiting measurement here. 71 has two significant digits, so we have to have two significant digits in our answer. If it was 71.0, then we would write this as 187. But in this case, it's only 71, so we write 190 as our final answer for this problem. Another situation, if we have a mass hanging on a spring, it is extending that spring, it's stretching that spring 7.9 centimeters, and we're asked to determine the spring constant. But we don't know the force directly. The force is Fg, so we have to actually calculate it. So Fg is 0.46 times 9.8. So this is our Fg, which equals our Fs, which equals K delta X. So we divide this Fg by 0.79 meters. That gets us our K value of 57.06, and we round to just 57 because of the two significant digits. Same spring. We have the K value. I'm going to leave it in my calculator. Now we're asked to calculate the displacement in centimeters of the same spring when we have a 0.75 kilogram mass hanging from it. So actually what I'll do is I'll store this in my calculator's memory so I can recall it whenever I need to. And what I have is a 0.75 kilogram mass multiplied by 9.8. So this is my force. I have to divide this by the spring constant, which was 57.06. I use the exact value, and I get 0.1288. I have to round for two significant digits where I get 13 centimeters. So I could have gotten this just by using the estimated value of 57. But notice there's a slight difference, and sometimes that slight difference gives you an incorrect magnitude at the end. So it's important to use the exact value when you're doing your physics problems, and only report your when you're reporting your answers, you would only then round to significant digits. So these are, we kind of glossed over this a bit, but most of these springs that we deal with are what we call Hooke's law springs that obey Hooke's law. There are springs that do not obey Hooke's law, but in most cases you'll see that they do. In this case, what we have is a force extension graph, and you can see that in a Hooke's law spring, the area underneath that graph is actually important as well, because imagine if we multiplied those two together, that would essentially give us our area. It's a force in newtons times the x, which is a displacement in meters, and every time we multiply newtons by meters, we end up with joules. So this might help you understand that the stored potential energy in the spring can be calculated by finding the area underneath the curve, and in this case it's a straight line, so the area underneath that is a triangle. And if we are going to calculate that area, it ends up being 1/2 the base times the height, or 1/2 of x times, or delta x times FA. So that is our elastic potential energy. We write that as E with a subscript E, capital E, to just differentiate it from electrical. So E is the area under the Fx graph. And for a Hooke's law spring, which is what we'll deal with mostly in this course, that area is 1/2 of kx squared. So we could also, I should have say, it's 1/2 of FA times x, but we could substitute FA is also equal to kx. So 1/2 of kx times x gets us to 1/2 kx squared. Quite often we drop the delta just for ease of writing, but technically it's a delta x. So here's our elastic potential energy. It should be E capital E with the subscript. It's the energy possessed by a perfectly elastic material. E capital E is the elastic potential energy in joules. K is the spring constant, and delta X is the displacement. So let's look at this problem. It says we have a spring with a spring constant of 75 newtons per meter. It's resting on a table. The spring is compressed a distance of 28 centimeters. So what is the increase in its potential energy? So this is 1/2, or 0.5, times K times 0.28. I have to put that in meters squared. Gets us to 2.94, and I report it as 2.9 joules. Now it says, what force must be applied to hold the spring in this position? So I don't actually need the 2.9 joules to solve this. Going back to the two values we had from the initial part of this question, 75 and 28 centimeters, force is equal to K delta X. So 75 times 0.28 gets me to 21 newtons. Here's another problem. So this problem says a 5.3 kilogram mass hangs vertically from a spring with a spring constant of 720 nanometers, newtons per meter. The mass is lifted upward and released. So calculate the force and acceleration of the mass when the spring is either compressed by 3.6 or stretched by 3.6. So for both of these problems, A and B, we have the same givens, except our x kind of is treated in a different direction. But our spring force is K delta X, and our force of gravity stays the same for both. So let's look in the first case where we have A, where our delta X is positive because it's being compressed. So this is a F equals K, which is 720. I should say this is F net. F net in this case, let me redo this. So F net, the net force acting on the spring, if we look at the free body diagram, here's our object, there's our spring. You don't necessarily have to draw that, but our force of gravity and our Fs are acting in the same direction. This is for situation A. In situation B, our force of gravity and the force of our spring are acting in opposite directions. So in situation A, our net force is the sum of Fg plus Fs. And Fg is mg, Fs is K delta X. This is simply a substitute and solve problem. And if I solve this, I have 5.3 times 9.8 plus 720 times 0.36 gets me to 311.14. And I report my answer as 310 newtons. And I'd have to say the direction here. It would be going in the downwards direction because of both of my forces are pointing down. Now I need to then find the acceleration of this. And we know that F equals ma. So A equals F over m, which is 311.14. I use the exact value, divided by m, which is 5.3. So this value here divided by 5.3 gets me to 58.7, or 59 meters per second squared down. That's the solution to this and to that. Now over here, doing this for B, my F net is equal to the FG minus the FS. Rather, in this case, the FS is going to be more positive. So I'll write it this way, FS minus FG. This way I'll get a positive answer. So this is then 720 times 0.36 minus 5.3 times 9.8. 720 times 0.36 minus 5.3 times 9.8. This is 207.26 newtons, and I report the answer as 210 newtons up. And then again, I can find F equals ma, A equals F over m. A is equal to 207.26 divided by my m, which is 5.3. So I divide this by 5.3, and I end up with 39 meters per second squared up. So the last thing to mention, I did mention this a little bit earlier, about non-Hooke's law springs. So a perfectly elastic material, actually this is a bit of a different point, but that's okay. It says a perfectly elastic material will return precisely to its original form after being deformed. However, no real material is perfectly elastic. Each material has an elastic limit. When stretched beyond that limit into the plastic region, the material will not return to its original shape. As a result, the material becomes permanently deformed. So you've probably experienced elastics in your everyday life where they lose their elasticity over time. The more you stretch something, once you stretch something past its non-elastic range, it actually deforms the spring, and this is any elastic material. And then the material then cannot go back to its original shape because it's been deformed. So that is something else to keep in mind. Now I did mention non-Hooke's law springs. You will see something like that probably in the reading in the textbook if you read through that. But I would maybe focus a bit more on solving the problems. And again, if you have any trouble, please let me know. Thank you.